otherwise your answer will not be correct. Now, receiver noise. Receiver thermal power is given by N thermal is equal to KTB, that is in watt. Receiver power calculations are usually done in dBm, so decibel relative to 1 milliwatt. There's one suggestion for every one of you that I have observed in past few years, that students do not have a very good and solid understanding of dB scale. So it is highly recommended that please go through some of the notes that I have uploaded on Canvas related to the conversion from linear to dB and then linear to dBm, and what these terms mean and what kind of understanding we will develop when we want to put dB scale or understand a value in dB scale. How does it change everything? That's highly recommended. So please go and have a look at the conversion table and how to convert and what does exactly it means. So by general definition of dBm, it's 10 log power 10 in power in watt divided by 1 milliwatt. So there is a standard conversion of dB to dBm. On dB scale, if you have a value, say x in dB, and if you add 30 in it, then your answer will be in dBm. Just do not consider this as a standard bracket, because that the definition of bracket in dB scale is different. I'm just giving you what I mean here is, if you have 10 dB and you wanted to convert into dBm, just add 30 in it. So 10 plus 30 is 40, so the answer will be 40 dB. Do not consider these brackets as standard brackets, because it will change the definition of dB scale. Therefore, N dBm is equal to 10 log KTB, that is noise power, over 1 into 10 power minus 3. So by using standard logarithmic calculations, it's 10 log KTB minus log 1 into 10 power minus 3, which will give us 10 log KT plus log bandwidth plus 3 log 10. With T referenced at 290 Kelvin, that is at that Boltzmann constant is a constant, our general thermal noise is minus 174 dBm plus 10 log band B. This equation is very useful for high frequency system noise calculation. So N thermal in dBm is actually equal to minus 174 dBm plus 10 log B. So consider this B to be 1 Hertz, then the noise will stay at 174 dBm. So this equation is kind of very useful for a noise calculation. Therefore, it is possible to trade bandwidth for thermal noise in a communication system. This is one very important calculation, that if we have small bandwidth, then the receiver noise will go low, or the receiver sensitivity that we will study in coming sessions will also be low. So the overall area in which a communication device will work will be higher. Just imagine if we are operating in bandwidth of 1 megahertz, then the coverage of our communication system is 1 kilometer, and if we decrease the bandwidth 1 megahertz to 0.5 megahertz, then there will be a direct impact on the coverage area. So it is fairly possible to increase the coverage of our communication system from 1 kilometer to 1.5 kilometer just by changing the bandwidth. As we have seen, noise calculation for receiver circuit can become pretty complex. Fortunately, the circuit noise contributed by a particular device can be defined using a figure of merit called noise figure of a device. So noise figure is a general definition that you will see in many data sheets when you will be uh, in a working or owning your company and trying to develop communication devices. Then if you get a communication a device, not a communication device to be precise, an electronic device that will be required inside your communication device, then you will see that that electronic device will come with a data sheet, and each data sheet will have its noise figure, generally in dB. It indicates the amount of noise generated in the device above the thermal noise. So we already know that what thermal noise is, we already have defined it, we have kind of proved what thermal noise will be, and we know what level it is and how much bandwidth will have impact on the thermal noise level. So the noise figure will give a clear definition of how much noise is generated over and above the thermal noise value. And the general thermal noise definition is done at room temperature or 290 Kelvin. So NF is equal to 0 would indicate a perfectly noiseless receiver. So it means that the only noise that is generated by the device is actually thermal noise at a room temperature. So the noise figure is 0 dB. Total received noise power, NdB, is actually addition of N thermal in dBm at a given temperature plus the noise figure. NF is the total system noise figure. The quality of information transmitted through a communication system depends upon the amount of distortion of the information signal. Noise is important whenever the amplitude of the processed signals are similar to those of existing noise. What really matters is not the signal level, but signal to noise ratio. It means I have given one example in the start of this noise lectures that if we have a simple sinusoidal signal and if our noise is very low, then we will be able to still get to know what this signal should look like if we just identify what noise is and just remove it from signal. However, if we have noise level very high, then the signal may get like this, and it would be a little bit difficult for us to identify whether it's a plain sinusoidal or something else, because there is a lot of fluctuation around the origin, so it would be very difficult to identify. So what really matters is not the signal level, but the signal to noise ratio. So for this kind of noise in blue, if I increase the signal level, then perhaps I will be able to get to a point where this noise will consider as very low noise compared to signal power, and I will still be able to get to what the signal to noise ratio will look like. Low signal to noise ratio indicate vulnerability to noise or weak signal, strong noise, while high signal to noise ratio indicate immunity to noise. Strong signal, weak noise. I will just draw another point here. If I have one signal and it is compared with another signal that has a little higher level, and my noise is constant, I will just put another color here, my noise is constant, then the S over N ratio for this first combination, that is this signal plus this noise, will be higher. Let us say it's 10 dB, and the comparison with is low, that is 10 dB, and comparison between this signal, that is high signal, with the same noise, I have, imagine, 20 dB. So an S over N ratio of 20 dB is better than an S over N ratio of 10 dB. That's what exactly is told in this point. That is, low signal to noise ratio indicates vulnerability to noise, and high signal to noise ratio indicate immunity to noise, strong signal and weak noise. Signal to noise ratio. Signal to noise ratio at the receiver input is defined as the ratio of average power of the received signal to the average power of the noise measured at the receiver input. It is expressed generally in dB, but it can also be given in linear terms, but we normally consider dB to be more appropriate. So signal to noise ratio is power of a signal divided by power of noise. If you put the same in dB, then it's power of signal in dB minus power of noise in dB. Let's get to an example. A TV picture of reasonably good quality requires a video signal to noise ratio in excess of 40 dB. It means signal is 40 dB above the noise level. Assume that the TV receiver has 12 dB noise figure and the RF bandwidth is 60 MHz. Then the noise power at the input would be minus 174 dBm plus 10 log B plus noise figure. Now minus 174 dBm plus 10 log B is what we have been calling previously an thermal in dBm, plus noise figure, that is an excessive noise generated by the receiver itself. So by our calculation, we came to a point that our total noise is minus 94.2 dBm. Now we know one thing, that our signal need to be more than 40 dB, but if my noise level is at minus 94.2 dB, then my signal level need to be at least minus 94.2 dBm plus 40 dB. If 100 microvolt of signal is received on the TV antenna, whose impedance is 300 ohm, then signal power at the output of my antenna would be V square upon R, that is 100 microvolt squared divided by 300 ohm. It will give me a signal power of 3.3 picowatt, which is, if I convert it into dBm scale, is minus 74.8 dBm. So you can directly write this formula in your calculator, And if you have a scientific calculator, then it's a standard logarithmic formula into 10 power minus 12 divided by 1 into 10 power minus 3. And if you put this whole equation into a scientific calculator, then it will give you a direct answer on minus 74.8 dBm. That is signal power. Therefore, the signal to noise ratio, that is S dBm minus N, minus 74.8 is what we get from here, and minus 94.2 is the noise level. Now, if we get to the answer of this equation or this calculation, then we have 19.4 dB. So the overall signal to noise ratio is 19.4 dB, but we know that we need a high signal to noise ratio to be able to get a good received signal. This would result in very noisy video input. Snow on the TV screen in an analog system or blue screen on a digital system. So, as a consequence of this discrepancy between the received signal to noise ratio or calculated what you got from the previous example and what is required, that is 40 dB, we will have a bad signal on analog television that is almost not used now, but previously in 1990s and early 2000s we used to have these kind of televisions in which a direct connection from antenna is is uh, is established, and the placement of that antenna actually give us either very good quality signal to noise ratio or bad quality or a bad signal to noise ratio that eventually translate directly into the quality of picture that we get. In digital systems, low signal to noise ratio or bad signal to noise ratio means no signal at all. We don't have, we will be able to receive the bits and bytes that are transmitted, so we will not get we will get kind of a blue screen on general televisions, and or we will get a no signal indication on our screens. So these televisions are not used anymore, but they used to be very popular in old days. You may remember or may recall or may not even recall. I don't exactly know whether you know these televisions or not, but the theory is the same. Theory is the same. So that's kind of more or less the end of our signal to noise ratio topic. In the next session, we will move to how noise is calculated, and different methods, and minimum discernible signal, and minimum required signal for a communication systems receiver to work properly. Thank you very much for listening, and have a good day.